All right, welcome back to another session of Jensen Does Calculus. We're working on your edulastic problem on function analysis. Based off the feedback that I've been getting, one of the things that I've decided to do to liven it up a little bit is warm you guys up with a joke so you can get really motivated. So here's your joke for the day. What is Mario and Luigi's favorite outfit? Denim, denim, denim. Woo! Slays me. All right, so here we go. Enough of the jokes. Let's do some math. And I know it's excited, and I'm excited to rock it with you guys. So the problem we got today, B2, is a function analysis type problem. On the function analysis problem, here's what they've given us. They've given us the graph of f, being this graph here. They've defined g of x as the integral from -1 to x of f of t dt. This is our accumulation function, so if you go to your accumulation notes, that may be helpful there. And then they've asked us to do a big old plethora of things. We have A through E, so we've got 5 parts we're going to knock out today. We're going to work on first just doing one piece at a time as opposed to trying to explain all of the pieces at once. Let's start here. On part A, we're going to do g of 4 and g prime of 4. Again, A is kind of like our intro here, which is kind of nice that we have something that we can do right away. Well, we're already going to find g of 4. What I'm going to do is I'm just going to put 4 into my g of x function. What that means, I'm going to do g of 4 would be the integral from -1 to 4 of f of t dt, which the integral of that, my f function, is defined here. Remember, the integral of f would be the area above or below the curve of the x-axis, okay? When I look at my f function from -1 to 4, that's from here to here on my graph. Notice that from -1 to 0, my area is below the curve, which will be a negative area, and then my area from 0 to 4 is positive. So what I'm going to do is break this integral up into 2 parts. I'm going to say that this is the integral from -1 to 0 of f of t dt plus the integral from 0 to 4 of f of t dt. This then we use basic geometric shapes. Because we don't have an equation to integrate, we're just trying to use our geometry to see if we can find a shape that will model this for us. So when I look at this one, from -1 to 0, you can see here that this forms a triangle. Remember, the area of the triangle is 1/2 base times height. The base being 1 here, the height being 6, and then half of that. So 1 times 6 would be 6, half of that is 3. So this is going to equal 3. But remember, this is below the curve, so this is going to be a negative area, or -3. Plus, then I got to do the area here between 0 to 4. 0 to 4 is here. So that is, again, forming a triangle in this spot here, which would be 1/2 base times height. I'm going to call my base 4. My height is 2. So 4 times 2 is 8, and half of that is 4. Let's use blue. And then I add these two numbers up, and -3 plus 4 is a positive, not -1, I can add. I promise I can add, is +1. So we got g of 4 is +1, no problem there. We're moving on to the second part of A, which is we want to do g prime of 4. In order to do g prime of 4, I need to take the derivative of g of x. So if I take the derivative of g of x, that's d dx of the whole thing, of g of x equals the accumulation from 1 to x, -1 to x of f of t dt. At this spot, when I get this, the derivative of g of x is g prime of x. And then this is one of our fundamental theorems of calculus, that the derivative of the integral, that these kind of like our inverse operations, or they undo each other, especially if this is just an x here, so that g prime of x is equal to f of x. So the nice part here now is when we want to find g prime of 4, we're going to put, that would be saying g prime of 4 is equal to f of 4. Well, luckily for us, we have the graph of f of x. So f of 4 is just the function evaluated at 4, or essentially the y value at 4, which is 2. And there we have it. We've answered part A, and we're going to move on to part B. Alright, so moving on now, we're on part B. Part B says we're trying to find the average rate of change of g from the interval -1 to 5. Remember, average rate of change for that would be, that's going to be g of 5 minus g of -1 divided by 5 minus -1. This is essentially, we're using the slope of the secant line is the average rate of change. At this spot now, this problem is actually pretty fundamental here. What we're going to do is we're going to find g of 5, g of -1, and we're going to subtract these numbers and get our answer. So, g of 5, remember this is our g of x function. This means we're putting in 5 for our x value. So that's going to be the integral from -1 to 5 of f of t dt minus the integral from -1 to -1 of f of t dt divided by 5 minus the -1, subtracting by a negative, same thing as adding, so that turns into a plus 1, which is 5 plus 1 would be 6. And now we're ready to go. We need to do this integral, the integral from -1 to 5 of f of t dt. Luckily, from part A, we knew that we found the area from -1 to 4. We already found that whole area to be 1. If you go back to part A. So going from 4 to 5, we just need to add this little extra piece in here to find that area. That is this piece of the triangle, which is 1 times 2, which is 2, divided by 2 is 1. So this area from 4 to 5 is 1, plus the area that we got from before. Let me show this again on the whiteboard here. This was -3. This here was +4. And this area here is +1. So when we're adding all of these up here, -3 plus 4 plus 1, that's our area from -1 to 5, which will be +2, minus the integral from -1 to -1 would be the area under the curve from -1 to -1, which we've learned is just 0. It's a goose egg. So that's just 0 divided by 6. 2 minus 0 is 2, and 2 divided by 6 reduces to 1/3, thus getting our final answer, and we're good with part B. Okay, we're back for part C. On part C, what they've asked us to do is to find the x-coordinate of the inflection point of our g function from the interval -0.5 to 6 as an open interval, and they need me to justify my solution. They need me to give you a reason why I know that's true. I can't just say, hey, the answer is 4 because I've done the problem, or I guessed and got lucky. So an inflection point is when our second derivative changes from positive to negative. So if I'm trying to find inflection points of g, I need the second derivative of g of x. So remember, if we take the derivative, and we showed this earlier, that g prime of x is equal to just f of x. We showed this part earlier. And so then g double prime, the second derivative of g, is equal to f prime of x. So if I want to find the inflection point of g, I want to know when this second derivative goes from positive to negative, or from negative to positive. That's the same thing as when f prime goes from positive to negative, or negative to positive. Well, since this is my f function, f prime would be the slope of this graph. And so we're looking for when this slope over the interval 0.5 to 6 changes from going up to going down, or when the slope goes from negative going down to positive going up. What we're going to do then is look at this and say, oh, I know on the interval from 0.5 all the way to 4, you can see that the slope of this function is positive. So I know that f prime of x is greater than 0 on the interval 0.5 all the way to 4. Okay? And then I also know that f prime of x is less than 0 on the interval from 4 to 6. So I can see that my function goes from increasing to decreasing. which is exactly what we need. So G double prime, or G of X, has an inflection point. Has an inflection point at X equals 4. This is my justification. I'm allowed to use F prime here because I defined F prime as equal to G double prime. Alternatively, you could have written G double prime here, going from positive to negative, proving the exact same thing. And there we go. We've answered part C for you. All right, here we go. We're on to part D now. We're almost getting our way through this. This is where I think D and E kind of levels up in the difficulty here. So we'll do our best to try to explain it I'll do my best to try to explain it as clearly as I can. Here, we're looking for the absolute max over the interval -2 to 6 of G of X. To find the absolute max, remember G of X is defined as the area, basically the area under the curve or for our F function. But notice our starting point is at -1, so that's going to kind of change it a little bit. Because G of X is defined that way, we're going to continue to remind ourselves that G prime of X is equal to F of X. This is how the accumulation function works. That I want to consider when is F of X positive or when is F of X negative to find this absolute maximum. One of the good ways to do this is to do a number line or a sign analysis like this, where we check our critical points. In this case, I'm going to do -2, 0, 5, and 6. My critical points here being when F of X crosses the x-axis, and then also my endpoints as well. Between -2 to 0, my whole function is negative or below the x-axis. Between 0 to 5, my whole function is positive or above the x-axis. And then from 5 to 6, it's below the x-axis, so it's negative there. So now we want to figure out what points we can consider for the absolute max here. Knowing, though, that our integral is starting at, critically, that -1 is our starting spot. So -1 being our starting spot means all the area to the left, my voice just cracked there, did you get that? All the area to the left of -1 here ends up being, negative area ends up being positive area, because that would be the integral from -1 to -2, which we know we can then write that as the negative of the integral from -2 to -1. This will end up making area that is normally below the curve. We would normally consider that negative area because our lower bound is -1. Now any stuff to the left of -1, this area becomes positive. Because of that, -2 is a consideration, is a possible point. In addition, although we have some negative area, all this positive area between 0 to 5 means that this is also a possible maximum. So that means that x equals 5 is also possible. These are also our possible values we want to consider. So, and then we don't need to consider 6 the endpoint because the area from 5 to 6 is all negative, and so there's no way we get an absolute max when we're adding negative area to that. So what that means now is we need to find essentially G of -2 and G of 5 and figure out which one of those numbers is larger. As we go and do that, here, I'll start by doing G of -2. So G of -2 would be the integral from -1 to -2 of f of t and dt. That's essentially then, like I said, negative the integral from -2 to -1 of f of t dt, which is equal to the area below the curve from here. So from -1 to 2, we can form this into a small rectangle, that area being there 2, and this piece right here. And then this is a triangle down here. So this area down here is, 1 by 4, and half of that because it's a triangle. This is 2 more. And below the curve would be negative, so 2 plus 2 is 4. So this is negative, and then evaluating this would be negative 4, and negative 4 ends up being a positive 4. So we have positive 4 as a possible absolute value at the x value of negative 2. The other one we want to check is we want to check g of 5. G of 5 would be the integral from negative 1 to 5 of f of t dt. Again, you're going to find the area under each of these shapes. Hopefully, if you've watched most of this video, we've already done this. We realized that this was 3, this was 4, and then this was, what was this? 2, this was 1 more. So this was 3, this was 4, and then this was 1 more. I guess I didn't have to break it into huge. I could have just done one big triangle, but that's how I did it. So negative 3 plus 4 is positive 1. Positive 1 plus 1 more is 2, which is what we got earlier. We got that was 2. So now we consider both x equals negative 2 and x equals positive 5 as our possible maximums, our absolute maximums. We can tell them which one's the absolute max by whatever one is larger. So we have an absolute maximum at x equals negative 2. Alright, welcome back. We're ready to move on to our last and final part. Before we do that, I got a couple quick announcements. My first one, on D here, they asked for what was the absolute maximum value. So I said it occurs at x equals negative 2, which is true, but the absolute value is 4. That was what we found as the area. So make sure you put 4 as the answer there. And before we start on part E, I know some of you guys at home are sitting there getting a little bit like maybe tired or a little bit sad that our time is coming to a close today. So let's do like a big good stretch. And right below right now you can give a thumbs up. You can click on that button. Mrs. Martinez and I decided that we're going to be giving some extra credit. Well, maybe not. But we're going to be giving some extra credit. Again, maybe not. If you just hit that thumbs up for me, put a comment down there. It's really, really helpful for feedback purposes. On to part E, our last and final part of this problem. On part E, they give us a brand new function. They tell me that h of x is equal to negative x times g of x. So as if f of x and g of x were not enough already, they give me a brand new freaking function. So, and they define it to be negative x times g of x. And then the question they asked was, when x equals 2, on h of x, do we have a maximum, a minimum, or neither? The way that we're going to be able to figure that out is we need to figure out the derivative of h prime, of h of x, which would be h prime, and see when x equals 2, does it in fact equal 0? If it does, then we have a possible critical point, a possible max or a min. To determine if it's a max or a min or neither, then we'll have to take the second derivative, h double prime, and put in 2. And when we put in 2 into h double prime, we'll see if the second derivative is positive, meaning concave up, negative, concave down, or neither, which would be like 0 or undefined, which means it would be neither. So, in order to do that, we got to find h prime of x. So let's get to work. As we go to do h prime of x here, it means I'm taking the derivative of this function. Taking the derivative of this function means I need to do the product rule. So I do the derivative of the first, which is negative 1, times the second, just g of x, plus the first function, negative x, times the derivative of the second function, which will be g prime of x. I can clean this up a little bit, and I'm going to write negative g of x minus x times g prime of x. My goal now is to evaluate h prime of x at the value of 2, so I'm going to find h prime of 2. So h prime of 2 means I'm putting in 2 into this function g of x, and I'm putting 2 into x and g prime of x. So it's going to be negative g of 2 minus 2 times g prime of 2. To find g of 2, that's putting 2 back into this function, which would be the area from negative 1 to 2. If you remember now, our final time here, this area here from negative 1 to 0 was 3, using the area of a triangle. And then from 0 to 2 would form this triangle here. That's 2 times 1, which is 2. Half of that, so this area is 1. So this will be negative, and then g of 2 is negative 3 plus 1 more is going to be negative 2 minus 2 times, now I need to do g prime of 2. Remember, we've written this a few times on there, but I'll write it again, that g prime of x is equal to just f of x. So if I want g prime of 2, that means I really am just asking for f of 2. F of 2 would be this function evaluated at 2, or the y value, which is 1. Go back to blue. And so then I get negative 2, which is positive 2, minus 2 times 1, which is minus 2, which is equal to 0. So when I did h prime of 2, I got 0. What that tells me now is that the slope of the function at 2 is 0, so it's possible now, this is a critical point, it's possible I have a max or a min of h of x at 2. The way that I can determine if it's a max or a min is I need to find the second derivative of h of x. So I need to find h double prime. So now I'm going to work on that part of it. So I'm going to rewrite h prime of x up here. Hopefully I've given myself enough room. H prime of x was equal to negative g of x minus x times g prime of x. So now when we find h double prime, I need a little bit more room, so I'm going to squeeze in here. H double prime of x means I'm taking this derivative. That will be negative g prime of x minus, now I got to do the product rule here. I'm going to do derivative of the first, so I'm going to treat the negative x as my first function, so I'm going to treat that as negative 1. So negative 1 times just the g prime of x. Plus the first one, negative x, times the derivative of the second, that's g double prime. Okay. So now my goal is to clean this up a little bit. That's going to be negative g prime of x, and then negative 1 times g of x, g prime of x is negative g prime of x again, and then this will be negative x times g double prime of x. Notice negative g of x, negative g prime of x and negative g prime of x will end up being negative 2g prime of x. Minus x times g double prime of x. So I found the second derivative of h of x, and that's what it is down here. I now need to evaluate this at x equals 2, so I need to put 2 in here. So h double prime of 2 is equal to negative 2 times g prime of 2 minus 2 times g double prime of 2. So that's going to be negative 2 g prime of 2. Remember, g prime is f of x. So g prime of 2 is the same thing as f of 2. As a reminder, f of 2 comes from this graph. It's just the y value when x is 2, which is 1. So this is going to be 1 minus, I got 2 times g double prime of 2. Now g double prime of 2, that would be the same thing as f prime of x, so it's going to be f prime of 2. F prime of 2, what that means is it means the slope of this line, of this graph at 2. So I need to know the slope here of this graph. That would be f prime of 2. Well, the slope is the change in y over the change in x, or old school terms would be rise over run. So if I go up 1 and over 2, I get that my slope here would be 1/2. Okay? Which means that g double prime of 2 is 1/2. And I got negative 2 here, and then negative 2 times 1/2 is negative 1, which is negative 3. What negative 3 tells me is that h double prime of 2 is negative. The second derivative tells us about concavity. At 2, if it's negative, that means our function is concave down. So if you do this concave down, and we had a slope of 0, concave down at a slope of 0 means that point will be a maximum. Okay, so we can finally answer our question here. Let's see if I can create a little bit of space here. We have a max, h of x has a max, a relative max, or a local maximum. I should write there, I don't have that room. I guess it has a local maximum or relative maximum at x equals 2, since we should tell our work, since h prime of 2 is equal to 0, and that h double prime of 2, h double prime of 2, sorry, not small, it was less than 0, h double prime of 2 is negative. That tells us that information. At this spot now, we've finished parts A, B, C, D, and E of this problem. Hopefully it made sense to you. Again, if you missed it in the beginning, just make sure you give me a big old thumbs up right below. Hit that like button for me. Write a comment. Give me some feedback. I'm really trying to grow in how I'm able to teach remote learning. And until next time, I'll see you guys soon.